Have you ever really thought about how our world is, well, held together? I mean, from the car you drive to the skyscrapers that define our cities, it's all connected by these powerful, but pretty much invisible seams. So today, let's dive into this absolutely essential technology, welding.
Yeah, when you think welding, this is probably the image that pops into your head, right? A crazy shower of sparks. But behind all that intense light is some serious science that literally fuses our world together. It's a process of creation, of strength, and just incredible engineering. So that gets us to the big question. When you need to join two pieces of metal, not just temporarily, but permanently, to make a single, stronger piece, how do you actually do it? The answer? Well, it's at the very heart of modern manufacturing. Okay, let's start with the basics. What is actually going on in that flash of light? It's all about forging a permanent metallurgical bond. Right, here's the official definition, but the keyword, the one you need to remember, is fuse. Welding uses incredible heat to melt the base metals, a lot of times with a filler material, and that creates this molten pool that cools into one solid piece. The crazy part? That joint can actually be stronger than the original metal. And this highlights a super important distinction. Welding is not the same as brazing or soldering. You can think of those two as using a really, really strong metallic glue. They only melt a filler metal between the pieces. Welding is on a whole other level. It melts the base metals themselves, turning them into a single unified part. And that is where that incredible strength comes from. Now, there isn't just one way to weld, not even close. You should think of it like a toolkit. And that toolkit is huge. I mean, there are processes using everything from gas flames to lasers. But let's look at three of the most common methods, just to see how engineers pick the right tool for the job. First up, we've got shielded metal arc welding, but everybody just calls it stick welding. This is the rugged, get-it-done workhorse of the industry. That stick is a consumable electrode, so as it melts, it actually provides the filler metal for the joint. At the same time, this special flex coating on the stick vaporizes and creates a protective cloud of gas. That shield is what protects the molten metal from nasty contamination in the air. It's a pretty brilliant all-in-one solution. So why would you choose stick? Well, because it's portable, it's pretty cheap, and it's fantastic for working outside where, a bit of wind might blow away your shielding gas if it came from a tank. It is the go-to for farm repairs, construction sites, basically any situation where you just need a simple, tough solution for joining steel. All right, now let's flip the script completely. We have TIG welding. Just look at the differences here. The tungsten electrode is non-consumable. It doesn't melt. It's just there to create a super precise, stable arc. The welder then uses their other hand to carefully feed a totally separate filler rod into the molten pool, and instead of that flux coating, you get a continuous stream of inert gas, like argon, from a tank to shield the weld. This separation of tasks is what gives the operators such incredible control. And that control is exactly why you'd use it. TIG is all about precision and quality. When you're working with thin aluminum on an airplane or you're creating those beautiful, clean welds on a high-end bicycle frame, this is the process you pick. Yeah, it's slower, and it definitely requires more skill, but the results, they're just unmatched. And now for something totally different again, resistance spot welding. This uses no filler rod at all. Instead, it clamps two pieces of sheet metal together and just blasts a massive electrical current right through them. The metal's own resistance to that current generates so much heat that it melts a small nugget and fuses the sheets together. This, right here, is the secret behind modern mass manufacturing. Why? Two words: speed and automation. A typical car body has several thousand spot welds, and they're all done by robots in just a matter of seconds. It's unbelievably efficient for joining thin sheets of metal when you need to make a lot of something very, very fast. Okay, so we've fused our metal. The weld itself is incredibly strong. Job done, right? Well, not exactly. This is where the real engineering challenge kicks in. See, the problem isn't always the weld. It's the area right next to it. Let's look at this cross-section of a weld. This diagram is everything. In the middle, you've got the fusion zone. That's the weld itself. On the far sides, you can see the original, totally normal base metal. But look at that area in between. That's the heat-affected zone, or haze. And this is the part that matters. The metal here didn't actually melt, but the intense heat from welding basically cooked it, changing its properties forever. So here's the paradox. The weld itself, the fusion zone, it cools down and forms a really strong cast-like structure. But right next to it, the HAZ has been fundamentally changed. Imagine taking a perfectly forged sword and just holding one section of it in a fire. Even if it doesn't melt, you've completely ruined the temper. That's kind of what's happening here. The carefully engineered properties of the original metal get totally compromised by that intense, uncontrolled heating and cooling. And why is that such a big deal? Well, that heat changes the metal's internal crystal structure, which can make it weaker or more brittle. As that area heats up and cools down super fast, massive internal stresses get locked inside. This combination makes the HAZ the most likely place for a welded structure to fail. So managing the HAZ, using techniques like preheating the metal or special heat treatments after welding, is a huge part of welding engineering. And this isn't just some theoretical problem in a textbook. The integrity of a weld and its surrounding area has very real and sometimes very high-stakes consequences out in the real world. Let's start with a major success story. This is the Marzi's Bridge in Poland. It was the world's first all-welded road bridge. Before this, huge structures were held together with tons of heavy rivets. Welding let engineers build things that were not only stronger, but also way lighter and more efficient. It was a complete revolution. But here's the flip side. The Titanic was a marvel, but its hull was held together by millions of rivets. And later investigations suggest that the failure of those riveted seams is part of why the ship sank so quickly. A welded hull, on the other hand, creates a single, monolithic piece of steel, a much, much stronger and more watertight design. So if we know that the heat-affected zone can be a weak point, and we know the consequences of failure are massive, how do we make sure a weld is actually safe? You can't just look at it and cross your fingers. You have to test it. Even with the most skilled welder in the world, things can go wrong. Tiny cracks can form, little gas bubbles can get trapped, creating porosity, or the weld just might not fully fuse with the base metal. These defects, which are often totally invisible, can be the catastrophic starting point for a major failure. This is where non-destructive testing, or NDT, comes in. It's a fascinating field, almost like engineering forensics. It starts simple, a visual inspection. Then, to find tiny surface cracks you can't see, they might use a special dye that actually bleeds out of any flaws. To go a bit deeper, they can use magnetic particles that cluster around defects near the surface. And for the ultimate check, they use ultrasound or X-rays to see right inside the solid steel, making sure the weld is perfect from the inside out. And of course, making sure the steel is sound is only half the battle. We also have to protect the skilled person who's actually creating the weld. This is a hazardous job. The arc produces intense UV radiation, which can cause serious sunburn and damage your eyes. There are toxic fumes, the risk of electric shock, and severe burns. So proper ventilation and personal protective equipment, PPE, they aren't just a good idea. They are absolutely non-negotiable. You know, welding has come a really long way from the old blacksmith's forge. So what does the future hold? Well, it's all about two things: automation and precision. We've already seen robotic spot welders, like this one here, in car factories, and that trend is only speeding up. Automation is just key. Robots deliver incredible speed and consistency, weld after perfect weld. They can also get into positions that are difficult or dangerous for a person, which improves both safety and quality. This combination of robotics and advanced process control is just pushing the boundaries of what we can build. So the next time you're crossing a bridge or flying in a plane or just looking up at a skyscraper, take a second. Think about those invisible seams. They're really a testament to this amazing blend of science, skill, and engineering that is quietly and very, very strongly holding our modern world together.